M2 muscarinic receptors, which respond to acetylcholine from parasympathetic postganglionic cells. We're going to have to do something else. My understanding is that these keep potassium open longer. So, if during this time there are potassium channels that are staying open, what's that going to do to the membrane potential? And it's going to hold it lower. It's going to be working against the funny channels, which means it's going to slow it down. Take longer to start the next action potential. So sympathetic speeds it up, parasympathetic slows it down. It's kind of neat to know the molecular mechanisms behind that. I think it is.
Can you repeat that? Making the next action potential.
It's slower to start it. How soon I start the next action potential depends on how quickly I get back to threshold. More potassium channels open is going to slow that down. And they can both be doing it at the same time. You could have both funny channels and more potassium channels, and they'll kind of tend to counteract each other. Remember, most of your organs get both sympathetic and parasympathetic, and it's just a shifting balance. Cool. Okay then. I think rather than going through the extreme detail, which we will eventually do on the conduction system, I'm just going to give you an overview of it right now. Okay, so here's our heart. Now, if I want the heart to have an organized contraction, which chambers should I have contract first? The atria or the ventricles? You could actually make either one work. But if the idea is that the atria push blood into the ventricles, making sure they're as full as possible, and then the ventricles shove all that blood out of the body to maximize how much blood we have, seems like the atria ought to go first. And really, the atria are not, strictly speaking, necessary. People can have what they call atrial fibrillation, where the atria are not contracting in a useful way, and be just fine with that. You can walk around with atrial fibrillation. Not exactly just fine, but that's not going to kill you. Your heart can still pump most of its output without the atria helping. But think of them as boosters. So they're going to squeeze extra blood into the ventricles, which are then responsible for squeezing it out to the rest of the circulation. So if we want the atria to contract first, which way should they contract? Upward or downward?
Down.
So we'd like the contraction to kind of begin near the top and go down-ish, right? Makes sense. Okay, but here's the problem. If we have that contract downward and it just passes on into the ventricular muscle, the ventricles are going to start contracting pretty much just as the atria contract. You're going to get the whole heart to contract more or less at once. Now, who would you guess is stronger? The atria have to push blood from here to here. The ventricles have to push blood from here to here. Who's going to be more powerful? Logically enough, the ventricle, especially the left ventricle, has to push blood through the entire body. So if these and these are contracting at the same time, is anything going to be moving from the atria to the ventricles? No. It would be a little like, imagine that door, okay, so that door swings this way, right? Yeah. All right, so imagine there's no latch. We are the ventricles. That's the atria. So if we both try to squeeze at the same time, and over there I have one person, and over here I have my entire class pushing on this door, is that door going to open? Not unless it's very strong. So if we push at the same time, this is useless. Nothing's coming in from the atria. Sorry? don't want the atria to be that strong. I didn't even mention why, but so maybe it would be better if when they squeeze, we let them finish, and then when they're done, then we do it. So we want to wait. We want the atria to contract, squeeze, and then when they start relaxing, then the ventricles can go. There's another slight problem. Which way do we want the ventricles to contract? Kind of that way. That's where the exit is. I mean, if you were to use toothpaste, you're not one of those monsters who squeezes the toothpaste toward the bottom of the tube.
Strong people will destroy.
Well, yeah, and honestly, if it just did this, it's probably not going to actually blow out the bottom of the heart, but it's still not going to be ideal. So, monster maybe not that bad. So, we want the ventricles to contract first, and then wait, and when they're done, atria first, wait, and then have the ventricles contract and squeeze that blood out. That would be nice. How are we going to get it to wait? We want the signal to start somewhere in the atria, move down, pause, skip to the bottom of the ventricles, and then go up from there. That's kind of tricky. How do we stop it from getting through to the ventricles? So, as it turns out, I'll sketch it out and then we'll do the detail next time. The base of the heart, this layer that has the valves in it, does not allow action potentials to get through. The muscle in the atria does not connect to the muscle in the ventricles directly. So if we get the atria to contract, if we spread a signal through the atria, it's going to stop there and not get through to the ventricles. We're going to have some autorhythmic tissue up near the top of the right atrium. This is known as the sinoatrial. Boy, you probably can't read that at all. Sinoatrial, or SA node. This is the thing that normally starts our heartbeat. That's going to spread a signal into the atrial muscle. It's going to spread out through the atria and cause them to twitch. We are also going to have, the problem here is this is not three-dimensional, so you have to imagine this is this is still in the atrium, it's kind of not either in front of or behind, you don't get that. Okay, another little patch of autorhythmic tissue here called the atrioventricular, or AV node, which is going to have a little tail that punches through that base, called the bundle of His. That bundle is going to travel down through the ventricular septum, the thing that separates the two ventricles, and the bundle branches to the bottom of the heart here, which confusingly is called the apex, which usually means top, but you know.
I think of it just as where it points.
Yeah, it's
like
the,
a whole lung.
The pointy bit.
The pointy bit.
Yeah, but it is called the apex of the heart for reasons that escape me. But, and from there, we spread out into the ventricles in a series of what are known as Purkinje fibers. I do too. Which spread the signal to the ventricles. All of that is autorhythmic tissue. All of that stuff is capable of generating its own action potentials, which is itself a slight problem, but we'll get to that. So the idea is the SA node starts the heartbeat and starts the atria contracting. The AV node is then going to send a signal down the bundle of His, through the bundle branches, to the Purkinje fibers, and into the ventricles, which are then going to contract. That's how we don't let it go straight from the atria to the ventricles, but we still have a slight timing problem. How do we make sure the SA and AV node are synchronized? There are a set of fibers that go from the SA to the AV node. Internodal fibers. But now we have our same problem again. SA node goes to AV node, which goes to ventricles, and there go the ventricles too soon. So we just need to add one more thing in. Sorry?
Is it just one?
Just one, sort of. You suspect that it might be more complicated than that? As it turns out, the AV node and bundle of His, which are really not fundamentally separate, they're kind of one thing, propagate action potentials very, very slowly. Right? When the action potential gets here, it actually takes a moment to work its way through that. I think of it as a little maze that the action potential has to get through. So let's do this.
So action potentials from the AV node down the bundle of His?
They're going to work their way through the AV node and bundle of His slowly, and then when they get to the bundle branches, they're very fast. So then branches to Purkinje fibers and back up is quick. So let's have it work like this. We will be the atrium. Y'all will be the ventricles. I like y'all. Okay. Yins. Isn't that something? Okay. You'll be my AV node. You'll be the bundle of His. And you folks will be the bundle branches, and we'll just ignore the Purkinje fibers for now. So, the problem we had, if we didn't have all that, is that now you're going to do the wave. And right now, pretend that the base is not there. You can do the wave across. So if I go, yeah, and there our signal, wait, keep going, you can go. It goes all the way to the ventricles, we have a problem. So instead, it's going to work like this. And we're going to do an extreme slow motion. I'm the SA node. So I go. Now you do extreme slow motion. Now pause for a moment. While they are starting to spread the signal through the atria, those internodal fibers have already taken the signal to you, my AV node. You receive it already before the atria has really gotten very far. And you're now slowly working its way across to her. So in the meantime, you do your thing in the atria. There they go. Good. Keep going, atria. Yes, excellent. And now when they start coming back down, that's about the time that you're going to pass it on to them. You folks go fast. And there go the ventricles.
Oh, did we go?
Isn't that cool?
Oh.
So we go. I am starting the heartbeat. The atria say, yes, we are the heartbeat. But at the meantime, we're going, I have started the heartbeat. I get it, you've started the heartbeat. Give me a second. Meanwhile, the atria are going, we are beating. And about the time the atria say, okay, we're done now. This says, done, boom. And the ventricles say, now we are beating. So it's nicely unified and timed. That little delay there is really important. So this also takes care of the problem that if this is all autorhythmic tissue, what's to tell the ventricles, what's to stop them from just saying, you know what, we're going now, and going before the, well, what stops it is the fact that this preempts that. SA node says, I have started, and AV node says, okay, we're starting now, rather than going off and doing its own thing. That does mean that the SA node has to always be faster than the AV node. AV node, will you help me with something? Okay. If this is the rate at which I send action potentials, clap at a faster rate than that. Good. Now, if every time she clapped, you all beat, keep going at that rate. If I'm doing this, we're out of sync. Even if she follows every time I do it, we clap, she claps, and then she claps again too quickly. Now, what I want you to do is, and what I would love to do ideally, which is not something I'm going to ask a student to do, is to say, this is my normal rate. I will always wait 2 seconds between claps unless the professor goes, at which point I will immediately clap, and then wait 2 seconds before my next clap unless he goes again. That's more than I'm willing to ask of you. So all I'm going to say is, when I clap, you clap. Okay? Okay, start at a nice slow rate. Now, if I'm the SA node, and I'm faster than her, and every time I clap, she claps, that's going to make sure that she is always following me. And if I stopped, you go back to your slower rate. But if I go again, she has to follow me. That's how the SA node maintains the heartbeat. Good job. Yes, I thought so. Well, except not that fast. That's like so. I understand. So why would we want the AV node to be autorhythmic at all if it's always going to follow the SA node? What advantage is there to this being able to generate its own rhythm? I don't know. Which part is more important, atria or ventricle? What happens if the SA node fails? The ventricles will still go. Yeah, if I am up here going, you're following me along, then I go, die, and the atria stop responding, you just say, and the ventricles go. So if something happens to the SA node and it stops going, the ventricles can keep going under the direction of the AV node because it is itself autorhythmic tissue. We don't want that usually, but it can. All right, good job. Now, we're doing our lab in the other room. I'm assuming if for any reason we don't have everything set up, I will move the open heart surgery video to today. But, sorry? You'd rather?